We left off with this slide right here, where we were talking about the reactants at one energy level going through a transition state where they had the correct amount of energy and orientation in order to form the products here. This right here is your heat of reaction. This right here is the additional energy that has to be added to the system in order to achieve this transition state. Now the temperature is a measure of the average kinetic energy of molecules. Higher temperature, higher kinetic energies. And so the higher the temperature, the larger the fraction of molecules that have the kinetic energy equal or greater to that activation energy EA. Once you have a larger fraction of molecules possessing that, that also means you have a larger fraction of collisions that will lead to a product formation. That larger fraction results in a higher rate of reaction. So consider this equation right here, where A is a constant called the frequency factor that's related to the frequency of collision and those with the proper orientation. You have your activation energy here, and you have your temperature at which you are measuring this particular rate constant. So the rate constant is going to depend upon this activation energy and the temperature. So let's look, for example, how this equation would apply for two reactions that occur at the same temperature. Each reaction has a different activation energy. So here you have, in this case right here, you have different activation energies. If you have a higher energy of reaction, the number of molecules on this axis you can see is much smaller than the number of that will actually be sufficient to achieve this, that will have sufficient energy in order to have the reaction take place. Whereas if the activation energy is only this at this level, a lower level here, that means that there you have, going over to this side, you'll see that the number of molecules is much greater than what you had down here for this one. So the lower the activation energy here, the greater the number of molecules that will have sufficient energy in order to have the reaction take place. Let's also look at the dependence upon temperature. Here you have two different temperatures. This is the lower temperature, and this is the curve for the higher temperature. For a given activation energy, you can see that at the lower temperature, there's a smaller number of molecules that have sufficient activation energy to react, whereas at the higher temperature, you have a greater number of molecules, right? That's exactly what this curve and these relationships mean. So this equation is called the Arrhenius equation. And what you can do is you can take the natural log of each side of this equation to give you something that can look more like at times like a linear function. This right here, your log of this A factor here, will be your x-intercept. This will be your y value. This 1 over r, well, this value right here, your activation energy over r, can be your slope of the line, and this right here would be 1 over t. So you would have plotting 1 over t on the x-axis will give you a straight line. If you have 2 points, if you know that what the values are at two different temperatures, you can get the ratio of those two rate constants. This form of the Arrhenius equation can be used with 2 K values and 2 corresponding temperatures to calculate what that activation energy is. So you don't need to know the value of the constant A to use this equation. You have to make certain the energy units on EA and R are identical. Okay, these have to cancel out. So here's a graph showing a linear relationship between K, the natural log of K, and a plot of 1 over T. And this right here gives the slope of this line, gives you the value of EA over R. Okay, and this particular one happens to be for the reaction of hydrogen iodide reacting to form hydrogen and iodine. So the probable mechanism for a reaction between NO2 and carbon monoxide, say that it means that you would probably have this sort of a transition state here, okay, so that you are left with this and this, NO and carbon dioxide. So this is a probable, and this is how chemists think of these things in terms of how must these interact for this to take place. Now, for something to have the right orientation, sometimes you need to have a catalyst. And a catalyst is substance that increases the rate of a chemical reaction by lowering the activation energy without itself being consumed by the reaction. A catalyst is regenerated in the process. So once it's used to form one set of reactants into products, those will move off and that can then be used for the next one. The catalyst provides an alternate reaction pathway with a lower activation energy. Sometimes the catalyzed path contains multiple steps, but each individual step has an activation energy that is lower than the activation energy of the uncatalyzed reaction. For example, if you were to start off and have a general reaction where you had the reactants here going to the products here, where you had to actually put energy into the system to have these products take place, and you may have a very high activation energy for that to take place. Instead, if you had a catalyst, it could lower it in a two-step way because you have one activation energy here. Following that, it has to reorient and with a separate catalyst or a different way of interacting with the catalyst to form this activation complex to end up with this product. So each time you have a peak, it means you have an activation complex and intermediate species. Okay, so that's what you would how you would interpret something like this, where this is the extent of reaction, how much you get to this point right here, and this is your overall energy requirement. And you can see that this is a much lower energy requirement here than you have for this one. This right here shows for two different catalysts or two different systems. Here is your extent of reaction for the first one. And you can see how high the energy value for this complex is. Here's your extent of reaction here. And you can see how much lower this is here. This is only at 20 kilojoules, whereas here it was over about 31 kilojoules. So catalyst B in this situation is going to give you a lower activation energy and be much better process for carrying that out. Here is one where you have a two-stage catalyst, and you can see that this first one, this first peak, is lower for this one right here than it is for this one. This one right here is unchanged. Despite that, because this first one is lower, this over here will have a lower activation energy for this entire operation. Okay, so there is a benefit and a lower energy requirement for this reaction catalyst than for this particular one over here. So a homogeneous catalyst is in the same phase of the reactant. It speeds up the reaction by forming reaction intermediates. A reactive intermediate reacts to form further to form a product and regenerate the catalyst. The reactive intermediate is formed but is immediately consumed. For example, chlorine radicals catalyze the decomposition of ozone. So if you have a chlorine radical here, now in other words, you notice that's not Cl2, it's just Cl by itself, so it's got a free electron there, reacts with this one to form ClO plus oxygen. Okay, and so this ClO then reacts with another oxygen molecule to form additional oxygen, regenerating this chlorine-free radical. So this right here would be considered an intermediate. Glucose 6-phosphate dehydrogenase is the rate-limiting enzyme for the metabolic pathway that supplies NADPH to cells. This is your energy supply for your cells. And so it's this particular enzyme, anything ending in ASE is an enzyme. It's a protein that forms an enzyme that reacts to help facilitate this metabolic pathway. The mechanism for the pentose phosphate pathway, and this is a G6, this is a glucose 6 PD, catalyzes the reaction that regulates NADPH, a coenzyme that regulates glutathione, which is an antioxidant that protects red blood cells from oxidative damage. So you've got one enzyme that works here, having glucose, forming glucose 6-phosphate, and then another enzyme here that reacts to end up giving you 6-phosphogluconate. And you also have another enzyme here that keeps shifting this back and forth between these two forms so that it can serve as a reactant up there. So it's a fairly complicated process, as are most processes involving the body. But enzymes are a critical component of all of these reactions in the body, and it behooves us to understand them. Now, a heterogeneous catalysis is in a different phase from that of the reactants. Most commonly, the catalyst is a solid. The reactants are in a gas or liquid phase. For example, a catalytic converter in automobiles consists of platinum and rhodium metals, and on them, carbon monoxide reacts with oxygen on this basis to form carbon dioxide. And the purpose of the rhodium metal is to have the NO forming nitrogen and oxygen. Both of these are good gases, contrary to what people might say. Carbon dioxide is essential for life and is not a pollutant. Carbon monoxide and NO both are ones that would be deleterious to life. So here is an example for the nickel catalyzed reaction of ethylene right here, plus hydrogen forming ethane. So ethene plus hydrogen forms ethane. So here you have hydrogen sitting on the surfaces of this nickel material. This ethylene can then come down and position itself adjacent to this, so that hydrogens that are adjacent then, can react with this carbon to form this material right here. Okay, and there are remaining hydrogen on board the surface here. So essentially you've got this pi bond here that is breaking and reacting with the hydrogens here to give you this molecule right here. And this is another one that is a very useful reaction involving heterogeneous, where solid phase here and the hydrogen and the ethylene are both in the gas phase, as is the resultant ethane. This is your dirty, quote unquote, dirty emissions coming in with your carbon monoxide and your NO gases in there, and coming out with the carbon dioxide and oxygen and nitrogen. So enzymes as biocatalysts, we talked about that just a little bit with that one example, and this gives you an example of how the lock and key approach, or the induced fit model, for how these things take place. And that pretty much wraps up what I wanted to talk to you about catalysis and the ends of this chapter. Let me know if you have any questions.